Okay, so we talked about two-port network previously, where we discussed various kind of ports and networks. One is called Z parameter, and one is called Y parameter. This is impedance parameter, and this is admittance parameter. We also talked about impedance driving function, or it's called driving point impedance. For a given port, what is the impedance? That is going to be known as a driving point impedance. We already talked about this. We also talked about one thing, Z11 and Z22 are actually impedances which are looking at the node or the terminals between 1 and 1 bar, and another one is between 2 and 2 bar, where these two will be input and output impedances. Z21 and Z12 are with respect to voltage, but the other terminals current, that is what going to be taken care. And generally, this Z21 equal to Z12, that kind of circuit is known as reciprocating network. So others are busy in Exodia or Mahima? Huh? Okay. And what is that? I have seen it, but I don't know about that. Okay. Yeah, I got one invitation also. Okay. Anyway, so I'm using these two books. So mainly this is our textbook, and this is our reference book. This is a little bit difficult, but after reading this, you should read this one. So whichever topic is important, I am covering from here, or I am taking some of the example so that you can understand things. But this book is mainly for the 17th number chapter of this book is dealing with the transistor model. But his way of talking about transistor is different than what I am teaching right now. Okay, so just for my information, can you identify kind of okay? So can you tell me the type of amplifier? I change a little bit. Let's write it down. Let's write it down -5. What about this amplifier? So let's look at the Q1 first. Hmm? Okay, you are saying that it's common emitter if you are looking at Q1 side. What about this one? Common collector. So it's common emitter plus common collector. Two kinds of amplifiers are there. Hmm? No, it's not cascode. That's why I kept this example. If you have something like this, then it's cascode. Common emitter goes to common. Okay, this is again. This is by the way two common emitters, not common. Emitter goes to common base. It's not common base, right? So common base happens when this is connected to some voltage and volt. Generally, okay. Do you know about this word? What is that? Hmm? Do you know about this word or this word? All are synonyms, by the way. If you know definition of one, like you know the definition of all. Yeah. So what is that, Gaurav? Huh? No, no, I'm telling you all are equal. All are equal. So if you know bias, then you can tell me. Do you know what is bias?
So regarding forward and
Hmm?
only know about forward bias and reverse bias.
Okay. So what is forward and reverse bias?
So in forward bias, diode is positive terminal diode.
Hmm. So you are saying that. So there are two conditions in biasing. One, when you want to keep this diode on, one in off, right? You can call them forward, reverse, whatever you like. But there are two conditions for biasing. And these conditions are happening with actually DC voltages. Am I right or wrong? These are the DC voltages when I am applying something more than 0.7 volt higher than the cathode side, right? Anode and cathode, if this is 0.7 volt higher than cathode side, this is forward bias, right? Means it's on. It might be have some resistance and all these things. We do not look at that. But we are either making on, off, two conditions are there. Similarly, for transistor, so this is called saturation region. This is called active. The one which is in third quarter, it's in cutoff. This side has to be, yeah, and this is for a given VBE. The whole characteristic is DC characteristic. The whole characteristic is DC characteristic, and let's assume that this is working at this point. Means for a given VBE of some value which is greater than 0.7 volt, I am going to observe some VCE that is also DC, and I am going to observe some current. If it is fixed at one point, that point is known as Q point or operating point, or the whole thing is having these conditions. This is known as biasing condition where it's working. Or I bias my transistor in on state or off state depending on this point. It might be here also. It might be here also. Right? So that is known as bias. Where you are biasing will make sure that your transistor is off, on, or like saturation mode, active mode, or in cutoff. Right? So it's depending on that condition. Similarly, like to you are doing in your diode, where you are making on condition, off condition, which you are calling forward and reverse. Same thing is happening here. Look. Same thing is happening here also, because there are two different junctions. Some other day I'll tell you, if you want to learn it, I can tell you why this is going to give you amplification, right? But internally it looks like this one: base, emitter, and collector. So when base to emitter is forward bias and this one is reverse bias, then and then you are going to have the amplification. Okay. So this is the amplification rule, or when this is going to happen, you are in active region. You know about this or no? Yeah, Mahima, do you know this? Okay. Maybe some other day we can talk about this, because this is not part of our course. Okay. So this is how it works. If you are in forward bias, this junction is forward bias and this junction is reverse bias. Okay, then you are in active mode of operation, or you have biased your transistor in active mode. Okay. So let's revisit what we have done it in Y parameter. Y parameter has two equations where I1 and I2 are dependent parameter or dependent variables, and v1 v2 are independent variables, right? And they are connected with each other by the y parameters, which are y11, y12, y21, and y22. Okay, so now my main interest of studies, we already know how to use y parameter, and I know how to use z parameter, right? There is no doubt, right? Today also we are studying only y and z, but you know all the basic fundamentals, how to derive z11, z12, and other quantities for z and y, right? For a given network. But it is not known to you how to use it in transistor. Okay. So if you understand biasing condition, okay, is there anybody who does not understand biasing? Eswara, can you tell me what is the biasing condition? Or bias or operating point or Q point? No, no, okay. Active is active mode of operation, like the one you are doing in diode. You are calling this forward bias. This one you are calling reverse bias. Similar to that, transistor is going to have three different region of operation. Three different region of operations are there. This region of operation is known as active. This region of operation is known as saturation. And this region of operation, when it's in third quadrant, it's known as cutoff. Hmm? Okay. Answering to Manpreet. Okay. This is the standard question people are asking in interview. Draw the characteristic of MOSFET and BJT. Okay. Those are look like similar to each other. But the basic difference between two characteristics is as follows. In MOSFET, when you want to make your transistor in on condition, means this side is known as saturation mode of operation, whereas in BJT this is known as saturation. That's the fundamental difference. And this is known as active, and this is look like a linear, so they call it linear mode or triode mode. This is, by the way, with respect to VC versus IC for a given VBE. This is ID versus VDS for a given VGS. This is just for your information. People will make confuse and ask you this question. So the saturation, which is here, it's here. By the way, MOSFET was invented much earlier than BJT. This is also for your information, and it got very popular after 2000. It's when people wanted to have everything in a small scale, so then they have taken MOSFET, or I should say, rather than MOSFET, they call it, or they are using it, CMOS. Have you heard about this CMOS? If you like switch on your laptop, you will see somewhere CMOS batteries and CMOS BIOS and all these things written with CMOS. CMOS must be there. So it's complementary metal oxide semiconductor. Okay. So these two are the. Is it answering your question? So I was not making mistake. Yeah, but thank you for this question, because this is a fundamental difference. People will ask you if you are targeting somewhere like TI or some circuit based company. So they will ask such questions just to start with. Maybe thereafter they are going to ask much more difficult questions. So Aishwarya, so active mode is the mode of operation. This mode of operation, if you are more than VTH, by the way, one more thing, look, this line is different than this line. This threshold line is different in MOSFET. Yeah, one side it's constant and one side it's different. So generally it looks like this. This line is different. This is just threshold voltage, but this is something else, VGS minus VTH. So when you are going to study that, then you will study this. Okay. So this is just fundamental difference. Okay. So we were here. So this is if your transistor having so much VCE, so much value of VBE for so much current, this point is known as active Q point or biasing point, biasing condition, biasing point or operating point. All are synonyms to each other. So it depends. If you are keeping here, your transistor is in saturation, but the value of IC, value of VCE and value of VBE. VBE is same because you are on same curve, but value of VCE and value of IC is changed. Are you following? There might be many curves depending on what value of VBE you are taking. As VBE is increasing, this curve is also changing. But if VBE is less than 0.7, you are in cutoff. Right? So there are two different points. If you are in saturation, you want to use this transistor as a switch. And if you are keeping in active, you are keeping your transistor in amplification. So it depends what exactly you want from your transistor. If you want amplification, you should keep your transistor in active mode, right? So let's assume one thing, you are interested in amplification. But however, okay, if I want to